Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. I am Dr. Azhar Ali, Assistant Professor, Electrical Engineering Department, Sarhad University, Peshawar, and you welcome back to this study. In this first video lecture of Week 10 for the course Applied Mathematics 1, today we are going to learn about the Rhodes Theorem. So first of all, I would like to tell you about the statement of Rolle theorem. For example, we have a function f that satisfied the following three hypotheses. Number one, if this function f is continuous on the closed interval ab, and second, this function f is differentiable on the open interval ab. And the third condition is f of a is equal to f of b. Then there is a number c in this open interval ab such that the derivative of the function at this point c is equal to 0. So a function will satisfy the Rolle theorem, will satisfy the hypothesis of Rolle theorems if these three conditions are satisfied. Now, before giving the proof, let's look at the graph of some typical functions that satisfy the three hypotheses of the Rolle theorem. The figure show on the graphs of four such functions, like you see over here in this slide. So this is the first graph. The graph of the function for the closed interval a and b, and this is here you see over here there are 2 points in between this interval c1 and c2. So this is the another graph for the function, and now in this interval you see over here there is 1 point c in this closed interval, and this is the another graph, and now in this interval ab you see over here this is the graph of the function. In this case the graph of the function is the straight line, and you see over here the graph of the function like a curve, and you see over here this is the third form of the graph of the function, and this is the fourth form of the graph of the function, and c is the point between the interval a and b. Now in all these cases, in each case it appears there is at least one point c f of c. So on the graph where the tangent is horizontal, and thus derivative of the function at x is equal to c is equal to 0. So there exists at least one point, and the coordinate of the point is c and f of c, and at this point this point on the graph where the tangent is horizontal, like you see over here, this is the tangent with the horizontal, this is the tangent is horizontal. So this is the another tangent is the horizontal, this is also the tangent, so that's why the tangent is horizontal, and you see over here in this graph the tangent also is horizontal. So in all these cases it appears there is at least one point c f of c on the graph where the tangent is horizontal, and the derivative of the function at x is equal to c is equal to 0. Now for example, we have a problem, we have a function f of x is equal to x square minus 2x plus 2 on the interval closed interval from minus 1 to 3. So we need to find a number c that satisfies the condition of Rolle theorem. So for the Rolle theorem, now this function if it is given there that the function f satisfied the hypothesis of the Rolle theorem, so we just to find the value we just to find the point between this interval. So f is continuous on the interval from minus 1 to 3, so this function f is continuous on this closed interval and differentiable on this open interval. Now furthermore, if we put a, this is the value of a is minus 1 and the value of b is 3, so f of minus 1 is also equal to 5 and f of 3 is also equal to 5. So Rule theorem applies, and it tells us that the derivative of the function must be 0 for some point where between x is equal to -1 and x is equal to 3. So the derivative of the function must be 0 at some point between this interval. Now you see over here, if we put x is equal to -1 in the function, we obtain 5, and if we put x is equal to 3 in the function, we obtain 9 minus 6 plus 2, which is equal to 5. So the hypothesis of the Rolle theorem that f of a is equal to f of b. So f of -1 is equal to f of b. So the third hypothesis of the Rolle theorem is also satisfied, and the function f is differentiable on the interval from -3 to 3, and the function f is continuous on the closed interval from -3 to 3, from -1 to 3, and the function is differentiable on the open interval -1 and 3, and f of -1 is equal to f of 3. So this function satisfied all the hypotheses of the Rolle theorem. Now there exists at least one point between this interval between -1 and 3 at which the derivative of the function is 0. Now since it is given that this function satisfied the conditions, satisfied the hypothesis of the Rolle theorem, so we take the derivative of the function, and the derivative of the function, like you see over here, the derivative of the function is equal to 2x minus 2. So the derivative of this function at some x is equal to c between the open interval will be equal to 0, because it is given that the function satisfies the hypothesis of Rolle theorem. So 2c minus 2 is equal to 0. Now if we calculate, then after simplifications we obtain the value of c is equal to 1. So the conclusion of Rolle theorem is satisfied by the number c is equal to 1, and c belong to this interval. C is equal to 1, which is between -1 and 3. Now another problem, they given that the function f of x is equal to x square minus x plus 5. Find all values of c in the open interval 2 and 4 such that the derivative of the function is equal to 0. So in this problem it is also given that this function satisfied the hypothesis of the Rolle theorem. So we just need to find the value of c between the interval. First we determine whether the Rolle theorem can be applied to this function f of x on the closed interval from 2 to 4. The function is continuous on the closed interval, and the function is differentiable on the open interval 2, 4, and its derivative will be equal to 0. So first of all, taking the derivative of the function, which is equal to 2x minus 6. Now the function has equal values at the end point of the interval. These are the end point. The end point of the interval is 2 and 4. So putting x is equal to 2, we obtain f of 2, which is equal to 2 square minus 6 multiplied 2 plus 5, which is equal to -3, and f of 4, we obtain 4 square minus 6 into 4 plus 5, which is equal to -3. So the third condition of the Rolle theorem also satisfied. F of a is equal to f of b, that is f of 2 is equal to f of 4, which is equal to -3. This means that we can apply the Rolle theorem for this function, and we can calculate the value in the open interval, which is c. Now the derivative of the function 2c is equal to -6. The derivative of the function at x is equal to c, and the derivative of the function at x is equal to c will be equal to 0, because the given function satisfied the hypothesis of the Rolle theorem. Now 2c minus x is equal to 0. Dividing both sides by 2, we obtain c is equal to 3. Actually 2c minus x is equal to 0 can be written as 2c is equal to 6. Now dividing both sides by 2, we obtain c is equal to 3, and this c is equal to 3 belong in this interval, in this open interval. C value, which is equal to 3, between 2 and 4. So hence the Rolle theorem is valid in this case for this function. Now another problem, to determine all the numbers c which satisfied the conclusion of Rolle theorem for the given function and interval. This is the given function is equal to x cube minus 4x plus 1 on the closed interval from minus 2 to 2. First we make sure that we can apply the Rolle theorem as we deal with a polynomial. This function is continuous and differentiable in the given interval. So this function is continuous on this closed interval and differentiable on the open interval minus 2 and 2. Now compute the value at the endpoints of the interval by using the hypothesis of Rolle theorem. So at the endpoint, f of minus 2 cube minus 4 into minus 2 plus 1, which is equal to 1, like you see over here. Now another endpoint, which is 2. So the function value at the endpoint 2 is equal to 2 cube minus 4 into 2 plus 1, which is equal to 1. So the value of the function at endpoints f of minus 2 is equal to f of 2. So this condition, this hypothesis of the Rolle theorem is also satisfied. Now the function has equal values at the endpoint, hence all the three conditions, all the three hypotheses of the Rolle theorem hold. Now to find the value of c, for the derivative, you see over here, derivative of the function x cube minus 4x plus 1, so 3x square minus 4. Now the derivative of the function at x is equal to c, 3c square minus 4. Now derivative of this function at this value is equal to 0 because the function satisfied the condition of Rolle theorem. So we can write 3c square is equal to 4. Now dividing both sides by 3, c square is equal to 4 by 3. Now taking square root, c is equal to plus minus 2 by under root 3. We obtain two value of c. One is called c1 minus 2 by under root 3 and other value is called c2, which is equal to 2 by under root 3, where the derivative of the function is 0. Both of them belong to the open interval minus 2 and 2. So for these two values, the Rolle theorem, in both cases the Rolle theorem is valid. Now mean value theorem. Lagrange mean value theorem MVT states that if function f of x is continuous on the closed interval AB and differentiable on the open interval AB, then there is at least one point x is equal to c on the interval such that derivative of the function at x is equal to c is equal to f of b minus f of a divided by b minus a. Now for the proof, you see over here, consider the auxiliary function f of x is equal to f of x plus lambda x. This capital F of x is equal to small f of x plus lambda x, and this is the graph of the function like you see over here. Now this is the chord and this is the tangent line at this point x is equal to c. Now we choose a number lambda such that the condition f of a is equal to f of b is satisfied for the Rolle theorem. Then f of a plus lambda a is equal to f of b plus lambda b. Now we can write f of b minus f of a is equal to lambda into a minus b, and this implies that minus lambda into b minus a is equal to f of b minus f of a. Now for the lambda, we can write lambda is equal to minus f of b minus f of a divided by b minus a. As a result, we have f of x is equal to f of x minus f of b minus f of a divided by b minus a into x. The function f of x is continuous on the closed interval AB, differentiable on the open interval AB, and takes equal values at the end point of the interval. Therefore, it satisfied all the condition of Rolle theorem. Then there is a point C in the interval, this open interval, such that the derivative of the capital F function at x is equal to c is equal to 0. Taking the derivative of the above function f of x, we get derivative of the function f of x is equal to if derivative of the small f function at x minus b minus f of b minus f of a divided by b minus a. Now capital F derivative at x is equal to c is equal to the small f derivative at x is equal to c minus b minus a minus f of b minus f of a divided by b minus a. And now this implies that small f function, or the function which is represented by small f, the derivative of this function at x is equal to c minus f of b minus f of a divided by b minus a is equal to 0, and this implies that the derivative of the function at x is equal to c is equal to f of b minus f of a divided by b minus a, and this is the proof of the mean value theorem. Now to check the validity of the Lagrange mean value theorem for the function f of x is equal to x square minus 3x plus 5 on the interval 1 and 4. This is the closed interval. If the theorem holds, find the value of c. C is a point satisfied the condition of the theorem. The given quadratic function is continuous and differentiable on the entire set of real numbers. So this function is continuous on this closed interval and differentiable for the open interval. Hence we can apply Lagrange mean value theorem, and the derivative of the function has the form like you see over here in this next slide. This is the derivative of the function x square minus 3x plus 5 derivative with respect to x. Using power rule, we obtain derivative of the function is equal to 2x minus 3, and this implies that derivative of the function at x is equal to c is equal to 2c minus 3. Now this is the mean value theorem. Derivative of the function at x is equal to c is equal to f of b minus f of a divided by b minus a. Now at the end point, b value is 4 and a value is 1. So f of 4 minus f of 1 divided by 4 minus 1, and this equation number 1. Now we calculate f of 1, which is equal to 1 minus 3 plus 5 is equal to 3, and f of 4 is equal to 16 minus 12 plus 5, which is equal to 9. Now the derivative of the function, like you see over here, this is the derivative of the function 2c minus 3. So putting the value of f of 1, f of 4, and the derivative of the function at x is equal to c, and this equation number 1, we obtain 2c minus 3 is equal to 9 minus 3 divided by 3. 9 minus 3 divided by 3 mean 6 by 3, and 6 by 3 is equal to 2. So 2c minus 3 is equal to 2. Now we can write 2c is equal to 2c is equal to 2 plus 3, which is equal to 5, and c is equal to 5 by 2. You can see that the point c is equal to 5 by 2 lies in this open interval. So in this case, mean value theorem is valid. Now another problem, we have a function f of x is equal to under root x plus 4. To find a point c that satisfied the mean value theorem for the function on the interval on this closed interval. So for the solution, you see over here, this function is continuous on the closed interval 0 and 5 and differentiable on the open interval 0 and 5. So the mean value theorem is applicable to this function. Now to taking the derivative of the function, you see over here, using the chain rule, so we can write derivative of the function is equal to 1 over 2 into x plus 4 power minus 1 over 2, and further derivative of the base. So the derivative of x is 1 and the derivative of 4 with respect to x is 0. So we can write derivative of the function is equal to 1 over 2 into x plus 4 whole power 1 over 2. Now this implies that derivative of the function at x is equal to c is equal to 1 over 2 into x c plus 4 whole power 1 over 2. Now since this is the mean value theorem, so for this theorem we calculate the function value at x is equal to b, and the b value is 0 for the given interval. So under root 0 plus 4, which is equal to 2, and the function value at x is equal to 5, we obtain under root 5 plus 4, which is equal to 9 under root, which is equal to 3. Now putting the value of f of 0, f of 5, and derivative of the function at x is equal to c in this equation number 1, we obtain 1 over 2 under root c plus 4 is equal to 3 minus 2 divided by 5, and this implies that 5 is equal to 2 into under root c plus 4. So taking square root on both sides, we obtain c plus 4 is equal to 25 by 4, and this implies that c is equal to 25 by 4 minus 4, which is equal to 9 by 4, and 9 by 4 is equal to 2.25. So you can see that the point C is equal to 2.25 lies in this open interval. So in this case, mean value theorem is valid. Now another problem, to find all points C satisfying the condition of mean value theorem for the function x f of x is equal to x cube minus x in the interval from -2 to 1. So this is a cubic function. We have here a cubic function which is continuous on the closed interval from -2 to 1 and differentiable on the open interval. Now for the derivative of the function, and this is the mean value theorem for the function, derivative of the function at x is equal to c will be equal to f of b minus f of a divided by b minus a. So we are searching a point c between the given interval at which these two sides, left hand side is equal to right hand side. This is the condition for the mean value theorem. So f of b mean to calculate the value of the function at the endpoint 1 and at the endpoint -2. F of a mean 2 and b mean 1. So first of all calculate the function at the endpoint a -2. F of -2 is equal to -6, and f of 1, putting x is equal to 1 in the given problem. So 1 cube minus 1, which is equal to 0. Now derivative of the function with respect to x, 3x square minus 1, and the derivative of the function at x is equal to c is equal to 3c square minus 1. So putting the values of f of -2, f of 1, and derivative of the function at x is equal to c, and this equation number 1. So 3c square minus 1 is equal to, f of 1 value is 0 and f of -2 value is -6. So -6 plus 6 divided by 3 is equal to 2, and now we can write 3c square is equal to 2 plus 1. So 3c square is equal to 3, dividing both sides by 3 we obtain c square is equal to 1. So c is equal to plus minus 1. Now in this interval, -1 lies between in this interval. It is obvious that only one root, c is equal to -1, falls within the open interval. So only just one value minus c is equal to -1 lies in this interval. But c plus 1 does not lies in this interval, does not lies between this interval. We are searching a point between this interval. We are searching a point between -1 and 1. So we are searching a point between -2 and 1. So -1 is between -2 and 1, but 1 is not between -2 and 1. So the rule value, the mean value theorem does not satisfy at c is equal to +1, and the mean value theorem is satisfied for this c is equal to -1. So in this video lecture, you see over here, the conclusion of this lecture is one is the Rolle theorem and other is the mean value theorem. In the Rolle theorem, like you see over here, there are three hypotheses for the Rolle theorem: that a function will be continuous on the closed interval ab, and the function will be differentiable. The function will be differentiable on the open interval ab, and the function value at the endpoints of the given interval will be equal. So if all these three conditions are satisfied, then according to the Rolle theorem, there exists at least one point c between this open interval at which the derivative of the function will be equal to 0. And for the mean value theorem say that the function will be differentiable on the closed interval, and the function will be continuous on the closed interval and differentiable on the open interval. Then there exists at least one point x is equal to c on the open interval between a and b, at which derivative of the function is equal to f of b minus f of a divided by b minus a. So this is the mean value theorem. Now this is the end of this segment. Thank you. Allah Hafiz.